Hello, my name is Jingyang Liu, currently a PhD student at Carnegie Mellon University. I'm very honored to get the opportunity to share our work on the topic of robust visual SLAM with integrated UW positioning for construction robotics. So localization is essential for construction robotics to effectively navigate and autonomously assist humans in a wide range of applications, such as component installation, surface finishing, and maintenance. But visual SLAM is one of the most well-adopted techniques for indoor localization. However, several environmental factors on job site can pose challenge to VSLAM. Firstly, construction job sites are not always texture-rich. Surface such as blank wall can negatively impact feature detection when multiple regions share similar color or reflectivity. Secondly, repetitive building components such as scaffolding can be self-similar with insufficient visual feature variations. So VSLAM is prone to fail due to the lack of distinctive feature points, visual ambiguity, and false matches. Also, construction sites can rely on temporary lighting or natural light. For area with low light, for example, shadows and inconsistent illumination, for example, we turn on off the artificial lighting, the visual SLAM may fail in feature tracking, leading to drift and errors in localization. And in addition, indoor job sites are not suitable for global navigation satellite system, GNSS, as GNSS signals can be blocked or weakened by walls and other obstacles. So to improve the robustness of VSLAM in such environments, this study proposed a multimodal localization system that integrates ultra-wideband wireless localization and inertial measurement unit into VSLAM system to mitigate cumulative drift and errors. By leveraging the synergies between UWB, IMU, and VSLAM, our multimodal localization can overcome the limitation of each sensing modality and providing robust localization in visually challenging construction environments. So UWB localization uses ultra-wideband impulses radio to measure the distance between the mobile and the stationary base beacons. So in this study, we set up 4 stationary base beacons. The 4 base beacons are synchronized and the position of each beacon is self-calibrated. The distance between the mobile beacon and the base beacon can be estimated by the time of arrival or TOA of UWB signals. Then we can use the multilateration to estimate the location of the mobile beacon relative to the 4 base beacons. And we use the average absolute distance between estimated and ground truth trajectory over timestamps to evaluate the accuracy of the system. From both the qualitative and quantitative results, we can see that VSLAM can provide reliable short-term localization when the environment contains rich, unique visual features and the trajectory is relatively short and closed. And the impact of the outlier from the UWB measurement can be significantly reduced by VSLAM. We then tested the robustness of the system in 3 scenarios. In the first scenario, region with minimal features, we designed a trajectory passing through a blank wall to evaluate the robustness of the localization system when distinctive visual features are insufficient. So we can see in the video, small errors in orientation or position estimation can lead to significant accumulated drift. When VSLAM fails to provide accurate estimation, the combination of UWB and IMU provides reliable and globally consistent range measurement and corrects the drift. Compared to VSLAM only and UWB only approaches, the multimodal localization system remains invariant to the environment with scarce visual features. In the second scenario, regions with repetitive pattern, we use a roller door as a target object to test if the localization system can remain robust when symmetric or repetitive scene patterns bring ambiguities for future correspondence. In the video, we can see that VSLAM only system fails to provide reliable localization due to visual ambiguities. In this case, outlier removal process before EKF fusion effectively avoids the interference of the VSLAM failures on the post-estimation. In the third and the final scenario, in consistent illumination, we set up 2 controllable illumination conditions, the dark environment and the normal environment. We define the artificial light of 300 lux as a normal environment and the 30 lux as a dark environment. When the lighting condition changes from normal to dark, VSLAM localization failed due to the visual feature extraction and the matching. When the lighting condition returns to normal, the accumulated error leads to significant drift. Meanwhile, we can also see that the UW-only localization in this case is affected by non-line of sight or N loss when the UW signal is obstructed by obstacles. The attenuation of UW signals leads to noise and inaccuracy in UW-only localization. However, IMU sensors as a complementary modality optimize UW localization when the current measurement is identified as an outlier. So the localization trajectory obtained using the multimodal model localization system remains robust when both VSLAM and the UW localization fail. In the future work, several directions can be further explored. So from the perspective of application, we envision the system can be deployed for tunnel construction and inspection. So localizing a robot inside a long straight tunnels can still be challenging due to darkness, dust, ambiguity, and so on. So taking ambiguity, for example, when a robot navigates through a long straight tunnel, it can be challenging to locate the robot since the measurement can be identical everywhere. So by combining UWB range sensor with other sensors such as LiDAR, we may achieve robust localization inside real geometrically generated tunnels. And hardware side-wise, in current experiment, we deploy 4 sensors to cover a room of 75 square meters. The increased area may involve more stationary UWB beacons. In the future work, an optimization approach for effective beacon layout can be investigated to enhance scalability. And finally, from the perspective of algorithm, in the future work, we can explore a tightly coupled filter that leverage the raw data of the UWB to achieve potentially better outlier detection. And thank you for your attention and time. And again, we'd like to express our gratitude to the organizers and reviewers for your thoughtful comments and a time and effort to make this workshop a success. Thank you.
Thank you very much.